Hey guys, it's Off1 here, and today we're going to be solving graph valid tree. In this problem, we're given n number of nodes that are labeled from 0 to n minus 1, so we're always going to be starting from node 0, and I think that's important to know. And we're also giving a list of undirected edges, and they want us to write a function to check whether these edges make up a valid tree. So what is a valid tree? Well, a tree has two properties, and one, it has no cycle, and two, it is connected. So what do these mean exactly? Well, no cycle, that's pretty straightforward. Let's say we have three nodes. We have a node up there, node here, and a node here. This would be considered having no cycle because if we traverse the tree, we'll never end up in a loop. But if we add an edge here, if we start from here and then visit its neighbors, we'll go down here. And if we visit this guy's neighbors, we'll go here. And then eventually we end up back here and we end up in an infinite loop. So that's what having no cycle would mean. This edge here cannot exist. Okay, so what does connected mean? Well, let's say we still had this tree here. This is a valid tree, but let's say we had one extra node just out here by itself. This would mean that the tree is not connected, and that would be an invalid tree. However, if you added an edge here, this would still be a valid tree. Also, I forgot to mention this. Undirected edges just means that the edges point to both ends. So there's no specific direction that it's going to. So we can go from this node to this node, and also from this node to this node. So here I've redrawn the example from the problem, and also I've rewritten the valid tree conditions. So let's see if these edges give us a valid tree. So first we have our edges 0 to 1. So we're going to have 0, and we're going to have our 1 node here. And because it's an undirected graph, the edge goes to both ends. So we can go from 1 to 0 and 0 to 1. But I'm just going to draw them as a straight line just to keep it simple. So our next edge is going to be 0 to 2. So we can draw a 2 node here, and we can connect that to 0. Then we have 0, 3. So now we're going to have a 3 node here. And then our last edge is going to be 1 to 4. So we're going to have a 4 node that is connected to 1. So just by looking at this, let's see if we can see if it's a valid tree. Well, it is connected because every single node is connected to something. And there are no cycles. So as you can see, we can go from 0 to 1 and 1 to 4. And there's no loop there. If you go from 0 to 2, no loop. And 0 to 3, there's no loop. But if we had an edge right here connecting 4 to 3, then it would be a loop, and this condition would not be met, so it wouldn't be a valid tree in that point. Also, let's say we had a node 5 over here just by itself, then it also wouldn't be a valid tree because this 5 is not connected to any of these nodes over here, so this condition would not be met at that point. So to meet this condition here, we should be able to traverse the tree and go through every single node just by starting at this point here, or any point really since it's an undirected graph, but let's just say we start at 0 because that's the easiest one. So if you can't visit every node starting from 0, then that means the graph is not connected. So again, if we had an extra node over here, we would never be able to visit this node starting from 0 because it's not connected to this tree. So we can say if all nodes weren't visited, then we can return false because it wouldn't be a valid tree. And now where it gets tricky is the second condition here, because if you remember, these are undirected, meaning that we can go from 1 to 0 and 0 to 1. So let's say we start at 0 and then we visit 1. Well, from 1, we're going to visit all the neighbors, so we would visit 4, and we would visit 0. And we would see that we already visited 0, so we would think this is a cycle, but that will be false. So we have to take care of this somehow. Well, it's actually not too hard. All we have to do is keep track of whatever node we came from, and not visit that node. So what I mean is, let's start from 0 again. Let's say we go to 1. So if we're at 1 now, we're going to visit 4, and we're going to see that 0 is our parent, so we don't want to visit that one again. So what we can say down here is, if our neighbor is our parent, then we don't want to visit it. So we can say don't visit. Or in other words, we can say that if our neighbor is not our parent, then we do want to visit. Okay, but now how do we actually keep track of whether we have a cycle or not? Well, this visit function here is actually going to be our DFS call. And in our DFS call, we're going to mark our nodes as visited. And the way we're going to keep track of that is by using a hash set. So for example, when we visit node 0, we're going to make a hash set. And we're going to store our node 0 in there because that means we already visited it. And then at that point, we visit the neighbors. So now we would go to 1, and then 1, we would add it to our hash set. And then we would go to 1's neighbors. First, we check if 0 is the parent, and it would be, so we don't visit that. And then we go to 4. 4 is not in our hash set, so we would add that. And then we can see that 4 only has one neighbor, and that's a parent, so we would not visit that. And then we pop back up to 0, and we visit the next neighbor. So now we would be visiting 2. And 2 is not in our hash set, so we would add that in there. And 2 has no neighbors, so we pop back up to 0. And then we would go to 3. And 3 is not on a hash set yet, so we can add that. So we can mark it as visited. And at this point, our DFS call is done because we would only do DFS for the node 0. And we already visited all of 0's neighbors, so that means there's nothing else to do. And then at this point, we would just return true, that it is a valid tree. And just to show you how the cycle detection works, let's draw an edge here. And let's say that we're at 3, and we visit our neighbors from 3. So we would check 0, but that's our parent. So now we would visit 4. And we see that 4 is in our hash set, meaning that we already visited it at some point. So that means this is a loop here. And as you can see it is, we can go from 3 to 4, 4 to 1, 1 to 0, 0 to 3, and then back to 4. So at that point we would return false, because it would be a cycle. Our time complexity for this algorithm would be O of V plus E, where V is the number of nodes, and E is the number of edges. And our space is going to be the same thing. So we're going to have O of V plus E, because we need to store the graph. The reason the time is O of V plus E is because we have to make the graph and traverse it. So now let's get into the code. So to start, I'm going to break up the problem into 4 different parts. So first we're going to make the graph, then we're going to populate the graph, then we're going to do our DFS call where we check if it's a cycle, and then we're going to call our DFS function. So let's start. First let's make the graph, and to do that we just have to initialize an empty hash map. And then from here we can populate the hash map with every node. So for I in range of n, then we can do graph map at the key I is equal to an empty array for now, because it could have multiple neighbors, so that's why we're using an array. Next we're going to populate the graph. And the way we're going to populate it is by going through the edges. So we're going to do for parent and child in edges, we're just going to append these to the array. So we're going to do graph map at the key parent, and then append the child to it. And we're going to do the same thing but backwards because it's an unidirectional graph. So graph map at child, and we're going to append the parent. So at this point our graph is populated, and now we can just call our DFS. And like I said, we're only going to call our DFS for the 0 node. So we're going to do if is cycle, that's what I'm going to call it, for 0. And we can say the parent for this one is just 0. It doesn't really matter what you put there, as long as it's not an actual node. You can put -1 if you want, but I'm just going to use 0. So if it is a cycle, then that means it's not a valid graph, so we return false. Okay, so now all we need to do is define our DFS function. And before we do that, we want to have a set to mark our nodes as visited. So we're going to have visited, and it's going to be an empty set to begin with. And then we're going to define our DFS function. So define is cycle, because we're looking for cycles. And we're going to pass in a child and a parent. From here, the DFS function can be broken down into 3 separate parts. So the first one is going to be our check conditions. Second is going to be our mark as visited. And the last is going to be called DFS. Okay, so now we can start defining our function. And the first thing we want to do is check conditions. So what's our condition going to be? Well, we know that if a node is in our visited set and we visit it again, then that means we're in a loop. So we can say if our child is in our visited set, we can just return true, because that means there's a cycle. And then if it's not in our visited set, then we can just add it to it. So we can say visited.add, and we're going to add our child. And then from here we want to visit all the neighbors for the child node. So we want to do for every neighbor in our map for the key of our child. Then we want to check if our neighbor is equal to our parent, then that means we don't want to visit that, because that would give us a false positive. So we can just skip this for loop if it is our neighbor. And then next we can just run our DFS for our neighbor. So we can do if is cycle for our neighbor node, and now our child becomes the parent. If that returns true, then that means there is a cycle for the neighbor, which means there's a cycle in the whole graph, which means it's not valid. So we can just return true here. And then if we make it past this for loop, then that means there is no cycle, so we can just return false. And then at the end here, if there is no cycle, we can return if n is equal to the length of our visited set. Because our visited set should have every single node, and n tells us how many nodes there are. So these two should be equal, and this should work. So as you can see, this code is pretty efficient, and now I'll go through the code manually. So here I've drawn another example, and I've made the graph already here just to save some time. So the part for this is complete, and populating the graph is also complete. So now if we look at our node 0 in our hash map, we see that the neighbor is 1, and that's correct. And then for 1, the neighbors are 0, 2, 3, and 4, so that's correct as well. And as you can see, we have a cycle here that we should be able to detect with this code. So now let's see. So we're going to have our initial visited set, which is empty. And to mark them as visited, I'm just going to check them off just to save some space. So now we're going to call our DFS function. So we're going to start at node 0. So we see that node 0 is not in our visited set yet. So we're going to mark it as true. So I'm going to check that off. And now we want to visit every neighbor for 0. And the only neighbor is 1. So now we go to 1. We haven't visited 1 yet. So we can just mark that as visited now. And then we're going to call DFS for all the neighbors in 1. So our first neighbor is going to be 0. But as we know, 0 is the parent. So it meets this condition. So we skip the for loop for that. And now we go to the next neighbor, which is 2. And for 2 is not our parent. So we're going to do this if statement here. And we're going to do our recursive call. So we're going to do is cycle for our neighbor, which is 2. And our child was currently 1. So now our child is equal to 2. And our parent is 1. So let's see. Is our child visited yet? No. So we mark it as visited. And then we go through every neighbor in 2. The first neighbor is going to be 1. And we see that's our parent. So we can just skip the for loop for that. And then our next neighbor is going to be 3. So now we check if 3 gives us a cycle. So our neighbor is going to be 3, and our child is going to be 2. So now we check if 3 is in our visited set, and it's not. So we mark it as visited. And then we go through every neighbor in 3. And our first neighbor is going to be 2, but 2 is our parent, so we can just skip the for loop for that. And now we are at 1. So now we see if 1 gives us a cycle. So now our isCycle function is going to be 1 for the neighbor and 3 for the child. So let's replace this, 1 and then 3. And now we check if our child has been visited yet. And it has, because we have this green check mark here. And at this point, we would return true for this function. We return true here. And that gives us a true statement here for this if statement. And then for the overall function, we return a false, meaning there is a cycle. And that is correct. If this video helped you in any way, please leave a like and subscribe. Thanks for watching, and I'll see you in the next video.